Hello everyone, welcome to Computer Science 190, lecture number 2. Let's get to the slides. Today we'll be talking about overview of the computers. Okay, so starting from today, what I want you guys to do is to take notes while you're watching this lecture, okay, and submit them by the end of the day, by midnight, before Friday, to Blackboard. Go to the Blackboard, there'll be something like lecture number 1 notes. Please upload the photos of your notes. Not just one photo or multiple photos. You can archive them if you want to. Please upload them to the to the Blackboard. Okay. Also, starting from next Monday. So on Monday, we're gonna have the first homework. Okay. I'll send you a separate email about that. And starting from next week, from next Thursday, we're gonna have quizzes. Okay. So as of now, all you have to do today is just to watch this lecture and take notes. Some people say that I'm speaking too slow. If that's how you guys feel, you can basically speed up the video on YouTube. You know, it's like when you go to settings and then playback speed, you can go to 1.25 or 1.5 if you want to. Completely up to you. Okay. Okay, let's get started. So one of the questions I'll be asking you is on the quiz, right, and on the midterm and on the final exam. What does CPU stand for, right? What does it do? How many bits in the byte? What is the difference between a high-level language and the assembly language? Okay, so those are samples of questions of the ones which I'll be asking you on quizzes and midterms and the final exams. Okay, cool. Let's get started. So hardware and software. Basically, all the computers, everything we know about computers can be split into two parts: hardware and software. Okay. Those terms which are in the red, you definitely need to know them. You definitely need to take notes for them because they will definitely appear on the quizzes. So hardware includes everything tangible, all the parts of the computer systems, right? Which is what? I don't know, motherboard, hard drive, SSD, CPU, right? So everything which you can touch, everything which you can feel, everything tangible is called hardware. Keyboard, monitor, system, well, I guess PC itself, right? Then the graphics card, SSD, all of that would be considered hardware. Software software includes programs, right? And what is a program? A program is a set of instructions for the computer to follow. Okay, so what is a program? Set of instructions for the computer to follow. Familiarity with hardware basics help us understand the software as well. As a hint, any text that is in bold, that is in red, which is underlined, may be important for an exam. That's kind of a hint for you. Moving on. Hardware and memory. So most modern computers have similar components, and they usually include input devices, such as keyboard, mouse, microphone, right? And output devices, a display screen, printer, processor, and two kinds of memory. So there are two kinds of memory. One of them is called main memory. The other one is called auxiliary memory. Okay. So usually, I remember when I was learning those terms, I kind of thought that the hard drive, back then we didn't have SSD. Hard drive is the most important type of the memory. So I thought main memory would be the most important one, which would be the hard drive, right? Unfortunately, that's not the case. And we'll talk about it a bit later. So the heart of the CPU, of the computer, right? So the most important component of the computer, which computer is not going to work without by any means, is the CPU, the processor, okay? Processor, also called CPU, which stands for Central Processing Unit, or the chip sometimes, okay? One of the examples will be Pentium processor. So what does the processor do? The processor processes, right? So what does it do? It processes, programs, instructions. Okay, so again, what is a software? Software is a computer program which basically contains of the set of instructions, like instruction number 1, instruction number 2, instruction number 3, instruction number 4. I remember when I was in high school, I was thinking for a long time, like, I know that on one hand, I'm playing video games, I'm watching some movies, I'm watching YouTube, and I'm watching some videos, right? But on the other hand, I know that inside of the computer, inside of the laptop, I know that everything which is inside is just a bunch of transistors. Huge amount of transistors, a couple of boards, they just somehow connected to each other, right? So how is that going to be translated from hardware, from those transistors, into something I can watch, I can play, I can see? That was a big question for me. But basically what it comes down to is that there is a CPU and it processes instructions, programs very, very quickly. Okay, no matter what I do, if I'm playing the music, if I'm playing like computer science, Counter-Strike, I used to play 1.4, I think. CS1, Counter-Strike 1.4, and then was 1.5, then was 1.6. Or Dota 2, just whatever, Fortnite, right, Far Cry, whatever you guys are playing right now. Yeah, anyway, so the processor in the very, very grand scale, it can only process very, very simple instructions. Those instructions may include add, sub, which stands for subtraction, div, which stands for divide, mul, which stands for multiplication, store, which means store to the memory, load, which means load from the memory, and stuff like that. So that is like very, very simple basic instructions. If you guys know what assembly is, assembly language, that's basically what processors are doing. Super simple instructions. However, processor processes those instructions very, very quickly, right? And that's why you have that like 3.94 gigahertz, right, which is the speed of the processor. So the bigger that number, the quicker the processor processes instructions. Yeah, the power of computing comes from the speed and program intricacy. Here we have Intel Core i7, right, and they're like a very, very old chip. By the way, if I ask you about if I ask you to provide an example of a specific processor, of a specific CPU, okay, please keep in mind that, for example, if you say Intel Core i7, that's a series, that's not really a processor. That's not an example of a CPU. If you say Qualcomm Snapdragon, that's also a series of processors. That's not a specific model of a CPU. If you say Intel Core i7, right, and especially if you give some like part number, that will be perfect. That'll be perfect. If you say Snapdragon, like Qualcomm Snapdragon, well, I don't know, 510, 610, that will be also an example of a specific CPU. Moving on. Memory. Okay, so what does memory do? Probably obvious, right? Memory holds programs, right? Data for the computer to process, and the results of intermediate processing. Imagine you write some kind of program which adds two numbers together, right? So let's say number A, which is 5, and number B, which is also 5, right? So the memory needs to hold the operation, the plus, right? How it's going to add one thing to another. That's one. So that would be the program. It also needs to hold the data, which means those two numbers, right? 5 and 5, what A is equal to, what B is equal to. And also when you compute that thing, when you compute the sum of two numbers, it also needs to hold the result. That's what the memory is for in a very, very basic words, in a very basic example. There are two kinds of memory, as I said before, main and auxiliary, okay? Now the question is, what is main, what is auxiliary, and what does it mean? Okay, main memory. Main memory is basically your RAM, okay? So the that memory which you have on your laptops, like, I don't know, 8 gigabytes, 16 gigabytes, or 32 gigabytes, or 4 gigabytes, that would be your RAM, okay? Working memory used to store the current program, the data the program is using, the results of intermediate calculations, right? So basically the idea is that your CPU has pretty quick access to the RAM memory, to the main memory, right? And auxiliary memory would be considered your hard drive or SSD nowadays, or yeah, the hard drives or SSD. And those guys are much bigger, but it takes much more time to access any data on the auxiliary memory. So main memory is usually measured in megabytes or gigabytes, right? For example, 8 gigabytes of RAM. RAM stands for random access memory, okay? And how do we measure the memory? We measure the memory using bytes, right? So byte is a quantity of memory. So when we talk about the memory, usually we mean main memory, which means we usually mean RAM. Let's talk about, for a little bit, about the bytes versus bits. Let me see, what was that? Yeah, perfect. The size. Okay, color would be this. Perfect. Okay, so 1 byte, right? 1 byte is usually spelled. So, I'm sorry, hold on a second. Okay. Okay, so 1 byte is usually spelled like this, 1 in capital case B, right? Now, there is also another type of measurement of the memory, which is called a bit, right? So it's usually spelled like 1b with a lowercase b, right? And 1 byte is equal to 8 bits, okay? Now, 1 bit contains a super simple, the simplistic type of memory, which can basically hold only 2 values, either 0 or 1. So something either exists or it doesn't exist. Either yes or no. That's kind of how memory works in the computers, right? And I'll probably go over that in this class a bit deeper later and in 226. So 1 byte is 8 bits, 1 bit is either 0 or 1, okay? And now, if we go, you probably heard of the term kilobyte, megabyte, gigabyte, right? So 1 kilobyte would be 1024 bytes, right? So it's not 1000, so you're probably thinking like kilo, like kilogram, right? It's not 1000, but it's 1024. Why 1024? That was just historically formed. Basically, in computer science, we just measure everything in the power of 2, and the closest power of 2 to 1000 is 2 to the 10th, which is 1024. Okay, just keep in mind that when you say 1 kilobyte, it's not 1000 bytes, it's 1024 bytes. Also, 1 megabyte, right? So it's usually 1 MB is equal to 1024 kilobytes. Okay. Now, 1 gigabyte is equal to 1024. Can you guess? Megabyte, like this. And then 1 terabyte is equal to 1024 gigabytes. Okay. Hope it makes sense. And then I think they're petabyte and so on and so forth. Yeah, can delete that. Perfect. RAM, right? So here is basically a picture of a chip. So that's approximately what RAM looks like. That is a chip, and it's usually like PCI Express, and you would insert that board into your motherboard, and that's how you get the memory. Auxiliary memory, okay? Auxiliary memory is also called secondary memory. Those would include disk drives, flash drives, USB flash drives, CDs, DVDs. Again, nowadays would be hard drives and SSDs, okay? That memory is considered to be more or less permanent, which is also called non-volatile or non-volatile. I pronounce it as non-volatile. What does that mean? So there are two kinds of memory, again, main and auxiliary, but also they sometimes be called non-volatile and volatile. So when we say non-volatile, that means it does not depend on the power, right? So check this out. When you have a hard drive, right? When you turn off your computer, the memory, the data which is on your hard drive is not erased, right? It's still there. So if you install some kind of a program on your computer, when you turn that computer off and then you turn it back on, that program is still there. That data is still there, right? So that's why it's considered to be non-volatile. When we say volatile, or volatility, that means when you turn off the power, the data disappears, unfortunately. For example, if you have RAM, right? You're playing some video game or you're editing videos, you're editing music, right? RAM stores some kind of information, and then when you turn the computer off, that information is erased, that's wiped out. That's how the RAM works. That's why RAM is considered to be volatile memory. It's usually measured in gigabytes, right? 50 gigabyte hard drive, for example. Well, but usually, I guess, nowadays would be 128 at least. Okay. So bits, bytes, and addresses. A bit is a single digit, right, with a value of either 0 or 1. A byte consists of 8 bits. Each byte in the memory resides at a numbered location called its address. Okay, so here's how the computer works. Each byte in the memory, in RAM or hard drive or just wherever that byte is located at, has its own address. It's very similar to your own home address. Like in order to, for example, if I want to send you a letter, if I want to send some kind of mail, some package, I need to know where your address is. For example, it can be like 315 Main Street, Florence, South Carolina, right, in a zip code. That's approximately what it's going to look like. Kind of similar. It works very similar way with the computers as well. So every byte has its own address, and that address is not like 315 Main Street. It's usually just a number. Okay, and now when the CPU wants to access the data, it just follows that address, gets the data, and like brings it back to the CPU and like does something with it. Multiplies, divides, adds, subtracts, something like that. Here's an example. Here's a picture of it, right? Okay, so that's like a so-called memory map. So that's basically kind of like a Google map or like maps on your iPhone. So here you have different locations, right? Different cells. Inside of that cell, you have 8 zeros or ones, right? Because one byte is either 0 or 1. Sorry, 1 bit is either 0 or 1. 1 byte is 8 bits, right? So that's why you have 8 zeros or ones, and those are the values of them. And here on the left you see the address. For example, 3021, 3022, 3025, right? So instead of like I don't know, let's say my name is Steve Rubin, and that'll be like if I wanted to provide my address, right? Over here on the left I would say 315 Main Street, Florence, South Carolina, and over here I would just say my name, right? So that would basically mean that I am located at the address of this. So that's the byte, that's the value of the byte, that's the byte address. Hope it makes sense. Storing data. Data of all kinds, numbers, letters, strings, characters, audio, video, even programs. They're always stored in zeros and ones. Okay, so that's kind of the probably misconception or dilemma. I thought how's it possible that I'm playing a video game but also in hardware everything is stored in zeros and ones, right? So basically what happens is that there are special systems which encode and decode, which basically transform those zeros and ones into video games and watching videos on YouTube. When more than a single byte is needed, several adjacent bytes are used. The address of the first byte is the address of the unit of bytes. Files. Okay, so what are the files? Files will be considered a large group of bytes in auxiliary memory. Auxiliary, not main. Files also have names. For example, I don't know, music.mp3. Files are organized into groups called directories or folders. Java programs are also stored in files. Okay, and they would be usually, for example, be like homework1.java. Java would be the extension, and homework1 would be the name of the file. What else? Hold on. Okay, yeah. Program files are copied from auxiliary memory to main memory in order to be run. Okay. Zeros and ones. Machines with only two stable states are easy to make, but programming using only zeros and ones is very difficult. Okay, so again, it was historically shaped and formed that way that machines only understand zeros and ones. There were some attempts called fuzzy logic to introduce a third state, like 0, 1, and 2, for example, but they failed. Anyway, computers, electronics, they only understand zeros and ones, right? Fortunately, the conversion of numbers, letters, strings, and characters to audio, video, and program is done automatically. You probably don't even notice, you probably didn't even think that inside of the computers there are like, I don't know, transistors, motherboards, and they only understand zeros and ones, right? And that's kind of the purpose. You as a user should not be even thinking about the fact that the data is being encoded and decoded, basically transformed from one shape to another shape. Programs. A program is a set of instructions for a computer to follow, right? We use programs almost daily. Email, word processor, video games, bank ATMs, all of them. So everything you use, like on your smartphone, on your iPhone, that's all just a bunch of programs, a bunch of instructions. So, which means that there is a bunch of software developers who created that program first, then they uploaded that to App Store, and then you downloaded that, and now you can use it. Following these instructions is called running or executing the program. Input and output. Normally, a computer receives two kinds of input: the program and the data that is needed by the program. For example, again, if I'm writing the code which is going to add two numbers together, right, I need to write the program first, and also computer needs to receive those two numbers to add them to each other. The output is the result produced by the following the instructions in the program. So you can kind of consider the computer to be a black box. Okay, so you supply some data on the left to the computer, right? Computer also loads the program to the CPU, so it basically performs the program using the data, and that produces some output. So for example, again, if I'm writing a program which adds two numbers, right? So the data would be those two numbers, A and B, 5 and 5. The program would be how to correctly add two numbers together, and the output would be the result of the program, which will be 10. Sometimes the computer and the program are considered to be the same unit, to be the same thing. Programmers typically find this view to be more convenient. Operating system, right? So I usually at that point ask my students, like, what kind of operating systems do they know? And the usual name, of course, Windows, Macintosh, right? But there is a huge amount of them. The rest of them are much less popular. For example, iOS, Android, right? Linux, all different distributions, tiny versions of Linux are also there. What else? What is it? Google Chrome OS, right? Yeah. And there is a huge amount of more which you never heard about. But of course, it's dominated. The entire world is dominated by Windows and Macintosh and Linux, especially Ubuntu. Okay, so as software developers, what do we do? Hold on a second. Yeah, so well-known operating systems would include Microsoft Windows, Apple's Mac OS, Linux and Unix, Linux is based on Unix. What software developers do, we write code, right? And that code is written there are a huge amount of ways to write that code, and you need to know a certain language to write that code. For example, in our class, we'll be learning Java. Java is one of the most popular, most dominating languages, computer languages in the world. You probably heard of C, C++, C#, Python, Django, Go, also a huge amount of them, and they're being developed every day. But Java, I would say Java, C, C++, they never die down. They never fade away. All other languages, they come and go, right? Python seems to be sticking here for a little bit, I guess. But like Ruby on Rails, I'm pretty sure it's gonna go. Yeah. Unfortunately, computer hardware does not understand high-level programming language, right? So there are two types of languages: high-level programming language and low-level programming language. High-level does not mean it's more complicated. It doesn't mean that it's kind of superior. No, high-level language, that means that it's more user-adaptive. That means it's a lot easier to understand how that works. And low-level language, that means it's very, very close to the processor. So again, the CPU, since it's a piece of hardware, it only understands zeros and ones. So back in the day, when CPUs were only developed, what people did, they were programming using only zeros and ones. So literally their code would look like 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, that's it. And it's super difficult to understand, of course. And for example, if you want to write a code which would add two numbers together, 5 and 5, right, and spit out 10, that would maybe take you, 100 lines. So 100 lines of zeros and ones. It's super difficult to do. Well, not 100, sorry, no. Well, I would say 7. Right, so usually that would be 7 lines 32 bits on each line, so 32 either zeros and ones on each line. And of course, it's very difficult to understand, like, and especially if you make a mistake there, like in some 0, some 1, it's very difficult to cache. And that's why at some point people said that, hey, like, that's very difficult. Let's just write some kind of programming language which would kind of look like English. And that's what Java is all about. Java is basically looks like English language. For example, if in Java we say print out, right, that actually means that some number will be printed out. And if we wanted to go to low-level language, we'll have to just like print. We'll just have to type like a bunch of zeros and ones. Yeah. Anyway, unfortunately, computer hardware understands only zeros and ones, so it does not understand high-level language. Therefore, a high-level language program must be translated into low-level language, right? So we write some code in Java. That code is being translated from high-level to low-level code. And that low-level code, those zeros and ones, are being run on the CPU. Low-level languages like assembly or machine code. Okay. Now, you probably heard of the word called compiler. Compiler. So what is a compiler? Compiler is that thing which translates a program from a high-level language to a low-level language the computer can run. Compiler. The verb would be to compile. You compile a program by running the compiler on the high-level language version of the program called source code. Compilers produce machine or assembly language programs called object programs. Okay. Compilers, most high-level languages need a different compiler for each type of computer and for each operating system. Most compilers are very large programs that are expensive to produce. When I was in grad school, we had a class called compiler construction. We were basically we were supposed to create our own compiler, which is very difficult to do. And at that point, I realized how probably how much respect those people deserve, because it's notoriously difficult to create. What else? I wanted to tell you something. Oh yeah, cool. So let's say you have a CPU. Let's say it's Intel Core i7. Okay, and people who created that CPU, which means people at Intel, right? Those guys, they basically described all the instructions for that CPU. So basically, they said something like this. Let's say 000 is going to mean to add two numbers. Let's say 001 is going to mean to subtract two numbers. Let's say 010, right? Because I cannot have two. I can only have zeros and ones. Let's say 010 would mean to divide two numbers. Let's say 011 will be to multiply those numbers, right? And then people who write programs, they have to buy the CPU, and for that CPU create programs. Okay, and that's, let's say, how people decided to do at Intel. But people at Qualcomm, those developers, they have nothing to do with Intel, and they don't have to rely on Intel. They may say like Intel sucks. They produce like horrible chips. In our case, in our like Qualcomm company, for Snapdragons, what we're going to do, we're going to make 001 multiplication, not addition. 010 will make it division, not subtraction. For 011, for example, it will be squared, right? So basically raise a number to the power of 2. So you can probably guess what I'm trying to say. Each producer, each manufacturer creates their own chips. Those chips, each one of the chips has its own instructions. And that is why people who create programs, they kind of have to create different version for their programs for each of the CPUs. And that used to be a huge problem like 30, 40, 50 years ago. Because if I write a software, right, some people may want to run it on Intel, some people may want to run it on again Qualcomm, some people want to run it on like TI. Actually, TI produces a lot of chips. For every manufacturer, I would have to create my own version, a different version of the software. Now it's difficult. It's not an issue anymore, but that used to be an issue. That used to be an issue back in the day. Okay. Yeah, so Java bytecode. The Java compiler does not translate Java program into assembly language or machine language for a particular computer. So Java actually solved that issue. Instead, Java translate program into so-called bytecode. Okay, so instead of translating the source program into zeros and ones, Java doesn't do that. What Java does, it translates the source program into a special version of lower language called bytecode, and that bytecode is machine independent. Hold on. Bytecode is machine language for a hypothetical computer, also called interpreter, called Java Virtual Machine. So here's basically what's happening. The way Java works is that it creates a Java Virtual Machine, which is basically a virtual computer. That virtual computer exists for every possible processor, and that's why Java developers, what they have to do, they write only one source code. And then, for example, if I'm running, I don't know, my Windows Intel processor, and I can send that to be run on your iOS, right? So iOS, I think Apple has its own chips for iPhones, right? So basically, what's happening is that if I'm creating the software using Java, if I'm creating software for my Mac OS, right, or for my Windows, I don't have to create a second version for another chip. I can create the source code. I can create the bytecode, I can compile, I can create the bytecode, and I can send you the bytecode. Since my bytecode will be run on the virtual machine, Java Virtual Machine on my computer, and that bytecode can be also run on your virtual machine, Java Virtual Machine on your iPhone as well. Since Java Virtual Machines are the same, they will be run exactly the same way. That is a huge advantage of using Java. A bytecode program is easy to translate into machine language for any particular computer. A program called an interpreter translates each byte code instruction, executing the resulting machine language instructions on the particular computer before translating the next bytecode instruction. Most Java programs today are executed using a just-in-time or JIT compiler, just-in-time compiler, in which bytecode is compiled as needed and stored for later use without needing to be recompiled. Basically, in very simple words, let's say I created a program which adds two numbers, 5 and 5, like any two numbers, right? I can compile that code, and then later, if I need to also use that program in some kind of a larger program, I will not have to recompile that program which adds two numbers. I can just use the compiled version of the program for another bigger program. Okay. Okay, let's a couple more slides. Compiling, interpreting, and running. Use the compiler to translate the Java program into bytecode, right? It's usually done using javac command. That would technically needs to be done if you were not using Eclipse. We will be using Eclipse. That's why you would not need to run the javac command, which stands for Java compile. You would also need to use the Java Virtual Machine for your computer to translate bytecode instruction into machine language instruction and run the result in machine language instructions using by the Java command. Okay, that's also something you would have to do if you were not using Eclipse. In our class, we will be using Eclipse. That's why we will not need to do that. We'll just run the hit the run button, like the play button, that triangle. You'll just need to run that, and that's it. It does everything for you. But if we're not using Eclipse, that's what you would have to do. But it's still important to know that there is a javac command which compiles the code, and there is a Java command which runs the code that has been already compiled. Portability, again, so why is Java so popular? After compiling a Java program into bytecode, that bytecode can be used on any computer with a bytecode interpreter and without a need to recompile. So again, I write my code, compile that, and send a bytecode to you. No matter what you're using, you will still be able to, Java Virtual Machine will still run it. Bytecode can be sent over the internet and used anywhere in the world. This makes Java suitable for internet applications. Class loader. Okay, just a couple of things you need to kind of memorize. A Java program typically consists of several pieces called classes. Okay. In our Computer Science 190 class, we'll only be working within one class. So there is one file, there'll be one file, one .java file, one class. but in more complicated situations, the program is going to consist of 2 classes, or 3 classes, 5 classes, 10 classes, 10 files. Each class may have a separate author and can be compiled separately. A class loader, also called a linker, automatically connects 2 classes together. So it's possible for me, for example, to write one class, write one piece of Java code which adds 2 numbers together, and write a separate piece of Java code which multiplies 2 numbers by each other, right? And I can split them, I can put them in 2 different classes, and then a class loader or linker is going to link them together, and then it's going to become one unit. That's the last slide for today. Compiling and running the program. So here's like what it's going to look like on a general scale. So we create and modify the source code, right? So we write the source code. It may look like something like this. Public class welcome, public static void main, and then print out welcome to Java, right? You don't really have to understand like everything here. Just know that what it does, it prints out to the console welcome to Java. Okay, so that's kind of the purpose of it. Source code. Then we compile the code using the command javac. So basically say javac welcome.java, right? Again, when we use an Eclipse, or when we click that run button, triangle, it's all done automatically. At that point, it's possible that we made some kind of mistake. If we made a mistake, Eclipse is going to underline it. It's going to tell, hey, like you made a mistake. Then we have to go over here, and then we need to modify the source code. If everything goes well, then that code is going to be translated into bytecode, which is this, and then we need to run it. We need to say basically Java welcome. Because welcome.java is going to be translated into the bytecode, which is just called welcome, basically the same file name but without extension. And then that bytecode is going to be executed, and what is the kind of the result of execution? The code is welcome to Java printed out in the console. If there is a problem with running this code, so compiling was fine, but running the code caused a problem, then we're just coming back over here. Eclipse is going to tell us, hey, you made a mistake, and we need to modify the source code and then just repeat the whole thing. Cool. Hope it makes sense. That's it for today. The first homework will be available soon. It will be due on Monday. I'll send you a separate email about that. Please let me know if you have any questions, concerns. There will be no lab this week. The labs are going to start next week. Okay. I'll see you guys later. Bye bye.